Hi, this is Physics 221, Mathematical Physics 1, and this will be a two-part video. In this lesson, we're going to discuss about matrices and vector spaces. So this is the first part of the lesson on your matrices and vector spaces. In this lesson, we first discuss general vector spaces and their properties. We then go on to discuss the transformation of one vector into another by a linear operator. This leads naturally to the concept of a matrix, a two-dimensional array of numbers. And the properties of matrices are then discussed, and we conclude with a discussion on how to use these properties to solve systems of linear equations. Let's define your vector spaces. Vector spaces are a set of objects or vectors. For example, you have your set of vectors A, B, C, which is said to form a linear vector space B if it follows the following properties. First, the set is closed under commutative and associative addition so that your A plus B is equal to B plus A. And associative, that is your A plus B plus C is equal to A plus B plus C. The second property is that the set is closed under multiplication by a scalar. When we say a scalar, that is any complex number, to form a new vector lambda A. The operator being both distributive and associative so that your lambda A plus B is equal to lambda A plus lambda B. And you also have your lambda plus mu times A that's equal to lambda A plus mu A. And you have lambda times mu A. You have lambda mu times A, where your lambda and mu are arbitrary scalars. The next property is that there exists a null vector 0 such that your A plus 0 is equal to A for all A. Next, multiplication by unity leaves any vector unchanged. That is, your unity 1 times A is equal to A. And lastly, all vectors have a corresponding negative vector, negative A, such that your A plus negative A is equal to 0. So these are the 5 properties of your vector spaces, which are a set of objects or vectors that forms a linear vector space V. Just some note, if we restrict all scalars to be real, then we obtain the real vector space, an example of which is our familiar three-dimensional space XYZ. Otherwise, in general, we obtain a complex vector space. And it is common to use the terms vector space and space instead of the more formal linear vector space. So when we are going to talk about the vector space or just the space, what we meant is the linear vector space. Another definition is the span. The span of a set of vectors A, B up to S is defined as the set of all vectors that may be written as a linear sum of the original set. That is, for all vectors, we have the span X is equal to alpha A plus beta B plus dot 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 plus sigma S. So this is the span of your set of vectors A, B up to S that result from an infinite number of possible values of the scalars alpha, beta up to sigma. Now, for this case, if X is equal to 0 for some choices of alpha, beta up to sigma, and uh, your alpha, beta, and sigma should not all be 0, to get X is equal to 0, that is if alpha A plus beta B plus up to sigma S is equal to 0, then if it is equal to 0, then the set of vectors A, B up to S is said to be linearly dependent. In such a set, at least one vector is redundant since it can be expressed as a linear sum of the others. If, however, this one is not satisfied by any set of coefficients other than The trivial case in which all the coefficients are 0, again, if the only way for this one to be equal to 0 is if alpha beta up to sigma is equal to 0, then the vectors are said to be linearly independent, and no vector in a set can be expressed as a linear sum of the others. If in a given vector space there exist sets of n linearly independent vectors, but no set of n plus 1 linearly independent vectors, then the vector space is said to be n-dimensional. In this lesson, we are going to limit our discussion to vector spaces of finite dimensionality. Let's define your basis vectors. So if B is an n-dimensional vector space, then any set of n linearly independent vectors, you have your E1, E2 up to En, forms a basis for your B. So your E1, E2 up to En, we usually call this one as your basis vectors or your basis. And if x is an arbitrary vector lying in V, then the set of n plus 1 vectors x, E1, E2 up to En must be linearly dependent, and therefore such that you have your alpha E1, beta E2 plus dot 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 plus sigma En plus chi x is equal to 0. And we have here linearly dependent vectors. This is equal to 0, where the coefficients alpha, beta up to chi are not all equal to 0, and in particular, your chi should not be equal to 0. So you have this equation again. Rearranging this one by moving your x into the other side of the equation, we may write x as a linear sum of the vectors ei as follows. So we can have it by this equation here. So what we did here was to transfer your chi x to the other side of the equation and then divide all your individual elements with chi. So we may write x is equal to x1 e1 plus x2 e2 plus dot 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 plus xn en, which is equal to the sum of your xi ei. For some coefficients of xi that are simply related to the original coefficients, where your x1 is equal to negative alpha divided by chi, x2 is negative beta divided by chi, xn is equal to, let's say, your sigma divided by chi, and so on and so forth. And since, as this one here, as you can see, since any x lying in the span of B can be expressed in terms of the basis, so we're able to write x in terms of the basis E1, E2, and En up to En, or the base vectors ei, the latter are said to form a complete set. Okay, so you have a complete set for your E1, E2, En up to x. The coefficients xi are the components of x with respect to the ei basis, and these components are unique since if both your x, which is equal to this equation here, and x with this equation here, then the components are unique because you have this sum of your xi minus iy, or yi times ei is equal to 0, which, since the ei are linearly independent, has only the solution, which is your xi is equal to yi for all I that's equal to 1 to up to n. Now let's redefine your inner product here in terms of your vector spaces. The inner product of two vectors, denoted by your bracket notation here, you have your bra A and B, is a set or is a scalar function of A and B. So again, this symbol here, this is what you call your bracket notation. So this one here, this is your bra And then this one is your ket. So this is bra, and this is your ket. For you to remember, you can do it like this. You have your bra ket spelled this way. So let's put a line here along your C. So that is your line. So your bra points to the left, and then your ket points to the right. So that is your bracket notation developed by or introduced by Paul Dirac, which will know more about him when you go to your quantum mechanics. So you'll see more of this bracket notation when you go to quantum mechanics, or if we still have time, we can discuss about this one, your quantum operators. So let's go back. The inner product of two vectors denoted by, in general, your bra A get B is a scalar function of A and B. For example, you have the scalar or dot product of vectors in real three-dimensional space, and your A dot B that's equal to AB cos theta. In effect, the notion of an inner product, which is your bra A ket B, is a generalization of the dot product to more abstract vector spaces. So this one, the dot product of A dot B is just in the real three-dimensional space. But if we extend your space into abstract vector spaces, then we have the inner product bra A ket B to generalize the dot product to more abstract vector spaces. Alternate notations for your inner product. You have the inner product of AB or the bra A ket B are your parenthesis AB or simply your A dot B. The inner product has the following properties. You have your bra A ket B is equal to the complex conjugate of your bra B ket A. So you cannot just simply exchange your A and B. So your bra A ket B again is equal to the complex conjugate of your B of your bra B ket A. And if you have your bra A ket lambda B plus mu C, so that is equal to your lambda bra A ket B plus your mu bra A ket C. We note that in general for a complex vector space, so we can extend this one such that your 1 and 2 imply that your bra A plus your bra lambda A plus mu B ket C is equal to your lambda star or the complex conjugate of your lambda bra A ket C plus your mu star or the complex conjugate of your mu bra B ket C. And your bra lambda A ket mu B is equal to your lambda star times mu bra A ket B. So for this case here, if you take out your scalars lambda and mu, then the first thing that you do is to take the complex conjugate of your first scalar lambda and then multiply it with mu and then multiply it with your bra A ket B or your inner product of A and B. Following the analogy with dot product in three-dimensional real space, two vectors in general vector space are defined to be orthogonal. So orthogonal if your bra A ket B or the inner product of A and B is equal to 0. So if this is equal to 0, then you call your vector space as orthogonal. And the norm of a vector A is given by the norm of A that's equal to the bra A ket A raised to the power 1/2, or this is just the square root of your inner product. And in general vector space, your inner product of your A and A or your bra A ket A can be positive or negative. However, we shall be primarily concerned with spaces in which your bra A ket A is greater than or equal to 0 or is positive, and which are thus said to have a positive semi-definite form. So this is your orthogonal definition, and then this is the norm of A. Let us now introduce into our n-dimensional vector space a basis E1 hat, E2 hat, up to En hat. So remember again that these are your basis vectors, or also your bases, that has a desirable property of being orthonormal. So orthonormal comes from the two words orthogonal and normalize. So orthonormal meaning the basis vectors are mutually orthogonal. That is, the inner product of your vectors is equal to 0, and each has a unit norm, or that is, the norm of your vectors is equal to 1. And it has, or for example, a basis that has this property, your bra ei hat get ej hat, or the inner product of ei hat, ej hat, is equal to delta ij. So here, your delta ij is the Kronecker delta symbol, and it has the following properties. Your Kronecker delta, your delta ij is equal to 1 if I is equal to j, for this case here, and it's equal to 0 for I that's not equal to j. So this is again your Kronecker delta symbol. We may express any two vectors in B as the following. So this one here, this is the component expression of your vector A. So your vector A is equal to the sum of your AI EI hat. So you have your scalar AI and then your basis vector EI hat from I is equal to 1 up to n. And then your vector B can be written as the sum of your BI EI hat. So again here your BI are n scalar, and then your EI hat are your basis vectors. And furthermore, in such an orthonormal basis, we have for any A, your bra EJ hat get A, that's equal to your AJ. And thus, the components of A are given by AI, that's equal to bra EI hat get A. We can write the inner product of A and B in terms of their components in an orthonormal basis as the following. So the normal, or the inner product of A and B given by your bra A ket B. Just for your reference, these are the components of your vectors A and then your vector B. So we just take the bra of this one and the ket of this one, which is, in this case here, these are the components of your A. So you have A1 E1 hat plus A2 E2 hat plus plus AN EN hat. This is your bra A. And for your ket B, so you have B1 E1 hat plus B2 E2 hat plus plus BN EN hat. So this is again your ket B. And from this property of your vector spaces, or from this property of your inner product, you have your lambda A, or your bra lambda A ket mu B, that's equal to your lambda star mu times bra A ket B. So you can also take out the scalars A1, A2, AN, and also the scalars B1, B2, Pn out of the inner product. And we can actually separate those with your I is equal to J, and then we can also take out those with I that's not equal to J, and separate the two. So just following from this, you can write this equation here. So you have the sum of AI star, BI, and then this is for the case where your I is equal to J. And then this one is for the case where your I is not equal to J. And from your Kronecker delta, okay, if I is not equal to J, then you have 0. So that means this one here becomes 0. And if this is equal, if I is equal to J, then this Kronecker delta here is equal to 1. So that means here, this one goes to 0 and this one goes to 1. So your inner product of bra A cat B is just equal to the sum of your AI star BI. And as you can see, this is just a generalization of the expression for the dot product of vectors in three-dimensional space. If you have real numbers, or if you're going to talk about in your three-dimensional space, this is just the dot product of A and B. And since we are extending this one to abstract vector spaces, so you have the sum of your AI star BI from I is equal to 1 up to n, which is your inner product of your A and B. Some useful inequalities. For a set of operators, or I mean for a set of objects or vectors forming a linear vector space in which your bra A cat A is positive, for all A, the following inequalities are often useful. First, we have our Schwarz inequality, which is the basic result and states that the magnitude of your bra A cat B, or the magnitude of your inner product, is less than or equal to the norm of A times the norm of B. So this is your Schwarz inequality, where the equality holds when A is a scalar multiple of B, that is your A is equal to lambda B. And it is important here to distinguish between the absolute value of a scalar, lambda, and the norm of your vector A. The next inequality that is also useful is the, the triangle inequality, which states that the norm of A plus B is less than or equal to the norm of A plus the norm of B. And then we have your Bessel's inequality, which requires the introduction of an orthonormal basis EI hat, where I is equal to 1 to up to n into the n-dimensional vector space. And it states that the square of the norm of A is greater than or equal to the sum, the square of the magnitude of your bra EI hat cat A, which can also be written as your bra A cat A is greater than or equal to the sum of the square of the magnitude of your AI. And the last, which is not actually an inequality, but this is also useful, is your parallelogram equality. It states that the square of the norm of A plus B plus the square of the norm of A minus B is equal to 2 times the square of the norm of A plus the square of the norm of B. So those are some of your useful inequalities. You have your Schwarz inequality, your triangle inequality, your Bessel's inequality, and the parallelogram equality. Now let's discuss about your linear operator. A linear operator A associates with every vector x another vector y, such that your y is equal to your linear operator A acting on x, or operating on x, in such a way that for two vectors A and B, you have your linear operator A times lambda A plus mu B is equal to lambda A plus mu A B, where here your lambda and your mu are scalars. And we say that your A operates on x to give the vector y. If we now introduce a basis EI, where I is equal to 1 to up to n, into our vector space, then the action of your linear operator A on each of the basis vectors is to introduce a linear combination of your basis vectors. And this may be written as your linear operator A acting on EJ, that's equal to the sum of your AIJ times EI. So you have a linear combination or a sum of your basis vectors. Here, your AIJ is the I component of the vector AEJ. So this is a vector, but this vector is produced such that you have your vector A acting on EJ. And collectively, the numbers Aij are called the components of the linear operator in the EI basis. So you have this equation once again, and in this basis, we can express the relation of y is equal to your linear operator a acting on x in the component form as the following. So first we write the component form of your y in terms of the sum. So that is given by yi, and then this is your linear operator a, and then we write your x in component form in terms of the sum. So you have xj, ej. So this is again your y, your a, and then your x. And we can have it like this, such that you have, since here your aej is equal to this one, we can rewrite it in such a way that you have the sum of your xj times the sum of your aij, and hence in purely component form, in this basis, we have this form here. You have your yi that's equal to the sum of your aij xj. Here are some properties of your linear operators. If x is a vector and a and b are two linear operators, then it follows that your a plus b times x is equal to ax plus bx. Your lambda a times x is equal to your lambda times a x, and your ab times x is equal to a times b times x. So this is associative. Okay, but in general, the product of two linear operators is not commutative. So you cannot change a and b in any way you like. So that means your abx is not equal to your bax. But it is associative, as you can see here. In an obvious way, we define the null or the zero operator. So this is your zero operator or your null operator. And then the identity operator. So this one here is your identity operator by the following. So your null times x is equal to 0, and your identity times x is just equal to x for any vector x in our vector space. Two operators a and b are equal if ax is equal to bx for all vectors x. And this will only be true if a is equal to b. If there exists an operator given by the symbol here, such that your a times the inverse of a, or your a inverse times a, is equal to the identity operator. Here again, your a to the negative 1 is the inverse of a. So you have the a inverse or the inverse of a. So what happens here is that if you multiply your operator a with the inverse of a, you get the identity matrix. We have seen that in particular, your bases ai, both vectors and linear operators, can be described in terms of their components with respect to the bases. If you remember, you have the equations wherein you have the summation. Those equations were your bases written in terms of their components. And these components may be displayed as an array of numbers called a matrix. Here we begin our discussion with matrices. If a linear operator A transforms vectors from an n-dimensional vector space, for which we choose a basis aj, that's j equal to 1 to up to n, into vectors belonging to an m-dimensional vector space with bases fi, where I is equal to 1 to up to m, then we may represent the operator A by the matrix given by this one here. Okay, so this one here, we call this one as a matrix. And this matrix has elements. For example, you have A11, A12, A12n, AM1 up to AMN. So this is your linear operator A described as a matrix. The matrix elements Aij are the components of the linear operator with respect to the bases ej and fi. So these elements here, in general, can be written as your aij. The component aij of the linear operator appears in the ith row and jth column of the matrix. So this is your rows. The horizontal lines are your rows, and then the vertical lines are your columns. So your component aij of the linear operator appears in the ith row and jth column of the matrix. For example, uh, your A11 component belongs to or appears in the first row and the first column of the matrix. Another example is your A22. So your component A22 of the linear operator appears in the second row and on the second column of the matrix. Again, these are your rows and these are your columns. So here, for Aij, I is for the rows and J is for the columns. The array has m rows and n columns, and thus this one is called an m by n matrix. So this is an m by n matrix. When m is equal to n, for example, if they are the same vector space, then we may represent A by an n by n or a square matrix of order n. For example, you have a 2 by 2 matrix, meaning you have 2 rows and 2 columns. If you have a 4 by 4 matrix, meaning you have 4 rows and 4 columns. If we have a 3 by 4 matrix, then we have a matrix where we have 3 rows and 4 columns. The component Aij, which in general may be complex, is also denoted by the symbol here. So you can have the parentheses of Aij. In a similar way, we may denote a vector x in terms of its components xi in a basis ei, where I is equal to 1, 2 up to n, by the array x that's equal to this array here. This one is called a column matrix because you just have a one column, or conventionally and slightly confusingly, a column vector. Here, this is your vector x, and these are the components of your vector x. So you have x1, x2, xn. The column matrix can also be written as your x is equal to x1, x2, dot, 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 xn. So this is an array where you have a transpose. And this one is called the transpose of a row matrix. Or the transpose of the row matrix is equal to this column matrix here. So you have this T here, meaning you transpose this matrix and you obtain this matrix here. So in either way, you can write your vector x in terms of this way or in terms of this way. This is a column matrix and this one is a row matrix. Now, these are some of the basic matrix algebra that you can do. So first we have your A plus B ij that's equal to aij plus bij. This is your matrix addition. Next you have lambda A ij that's equal to lambda aij, and this is matrix multiplication by a scalar. And you have A times B ij that's equal to the sum of aik bkj from k, and this is what you call your multiplication of your matrix. And we shall go to this one by one. Let's discuss your matrix addition. The sum of two matrices, which is we can represent as S, is equal to A plus B, is the matrix whose elements are given by Sij, that's equal to Aij plus Bij. For every pair of subscripts, I and j, with I is equal to 1, 2 up to m, and j that's equal to 1, 2 up to n. For example, if A and B are 2 by 3 matrices, that is, both your A and B have 2 rows and 3 columns, then your S is equal to A plus B is given by the following. So your result is also a 2 by 3 matrix. So your matrix S, for example, will now have these components: S11, S12, S13, S21, S22, and S23. And for your vector A, which is a 2 by 3 matrix, let's say it has components A11, A12, A13, A21, A22, and A23. And for your matrix B, you have B11, B12, B13, B21, B22, and B23. So we're going to add your two matrices A and B to obtain your matrix S. Okay, so what we do is just to add the components A11 plus B11, and that will be our S11. Next, we add your A12 and B12, and that will be our S12. Next, we add your A13 and B13, and that will be our S13. Next, you can add your A21 with B21, and that will be our S21. Then we add our A22 and B22, and that will be our S22. And we add your B23 with B23, or A23 with B23, and that will be our S23. So as you can see here, this one is your S11, this is S12, this is S13, this is S21, this is S22, and this is S23. So clearly, for the sum of two matrices to have any meaning, the matrices must have the same dimensions. For example, both be m by n matrix. If, for instance, you have your matrix A a 2 by 3, and then let's say that your matrix B is 2 by 2, then your A plus B will not be possible, because as you can see, your A is 2 by 3 and then your B is 2 by 2, and we said that for the sum of two matrices to have any meaning, the matrices must have the same dimensions. Either you both have 2 by 3 matrices, or you can have both 2 by 2 matrices. And matrix addition is commutative and associative, so you can change A plus B and it's just equal to your B plus A. Next, we have matrix multiplication by a scalar. The product of a matrix A with a scalar lambda is the matrix with the element lambda Aij. For example, you have your lambda times your 2 by 3 matrix A, which has these elements. What you do is just to distribute your lambda to each of the elements of your matrix A. That is, your lambda times A is equal to this array here with each of the element multiplied by lambda. That is, you have lambda A11, lambda A12, lambda A13, lambda A21, lambda A22, and lambda A23. Multiplication by a scalar is distributive and associative. For example, the matrices A, B, and C are given by the following. So you have matrix A, which is a 2 by 2 matrix with the following elements, and matrix B, also a 2 by 2 matrix with these elements, and your matrix C, still a 2 by 2 matrix with these elements. So find the matrix D, which is equal to A plus 2B minus C. So we have the sum of your matrix, and you have your, and then we subtract some C, which is just the opposite of your addition. And we multiply some scalar 2 to your matrix B. So what we do is just to write your matrix as a sum. So this is for your matrix A plus 2 times B minus C. Okay, so what we do is to add 2 plus 2 times 1 minus negative 2, and that will be your D1, 1. So you have 2 plus 2 times 1 minus negative 2. And next is you're going to add negative 1 with pies of 0 and then minus 1. So you have negative 1 plus 2 times 0, which is 0 minus 1. Okay. And then next we add or we solve for your D, for your D to 1. So we have your 3 plus 2 times 0 minus negative 1. And then next we have your 1 plus 2 times negative 2 minus 1. And that will be your D22 element of your matrix D. So we have here your D11, D12, D21, and then your D22. Simplifying, your matrix D is equal to 6 minus 2, or 6 minus 2, 4, and negative 4. So you can practice this video to analyze more the solution. Now we discuss the multiplication of your matrices. The product of two matrices, P, which is equal to A times B, where P is the matrix of the quantities formed by the operation of the rows of A on the columns of B. So you have here the operation on how you are going to do the multiplication of your matrices. So your matrix P, Ij, which is the matrix of the quantities formed by the operation of A and B, is equal to the sum of your Aik times Bkj, where k is equal to 1 up to n. For any I, that's equal to 1 to up to m, and then for j, that's equal to 1 to up to r. And take note of this one here. You have your case, okay? If you see those case there, what we meant by that one is that you can only multiply matrices with, first, they have, the column number of your first matrix should equal to the row number of your second matrix. Again, you can only multiply two matrices if first, or if the column of your first vector, which in this case here is k, is equal to the row number of your second matrix B, which is still this k here. So k on your A should be equal to the k with your B. And it may be written in matrix form as the following. So your matrix P, which is the matrix of the quantities formed by the operation of your A and B, has these elements. So, but before that, let's look at, for example, this one here. Your matrix A is a 2 by 3 matrix, and your matrix B is a 3 by 2 matrix. So you have here your I, K, and then your K, J. So as you can see, we have the same number of K's. So that means we can multiply these two matrices here. And as you see, or uh, let's look at the elements of your matrix A. You have A11, A12, A13, and then A21, A22, and A23. And then for your matrix B, you have B11, B12, B21, B22, B31, and B32. In the next slide, you're going to I'm going to show you how you're going to get your P11 of your matrix B. Again, let us just emphasize that it is clear that for this to be a meaningful definition, the number of columns in A must equal the number of columns in B. That is for your A, IK, and then your B, KJ, The K in your A, which is the column, should equal to the number of K, the row in your second vector or in your second matrix B. For example, if you have 2 by 4 and a 3 by, let's say a 3 by 4 for your B, we look at this one and then this one here for your A times B. You have 4 here and then you have 3, so that means you cannot do the multiplication of this matrix here. Now let me show you how you're going to multiply your matrices. Okay, so this is your matrix P with these elements P11, P12, P21, and P22. So let's take first your P11 and we're going to get what P11 is. So P11, as you can see, P11. So again, the first number is your row and then the second number is your column. So the row is 1 and the column is 2, or sorry, the column is 1 also. So the row is 1, the column is 1. So for P11, we are going to take your first row and your first column. So this is already in square here. And what we're going to do is like this. We are going to multiply A11 with B11, as you can see here, plus A12 times B21 here, and A13 times B31. So your P11 has the following, or your P11 is equal to your A11 times B11 plus A12 times B21 plus A13 times B31. So that is how you're going to take your, or to get your P11 element. Next, let's solve for your P12. So just for us to see, your P12 has row 1 and has column 2. So we're going to take your row 1, still this one, and we take your row 2, or sorry, your column 2, this one here. So your P12, we're taking this one, your P12, that's equal to A11. So again, that's equal to A11 times B12. So you can see here, plus A12 times B22. This is this one here, and A13 times B32. So you have this one here. So your P12 is equal to A11 B12 plus A12 B22 plus A13 B32. So that is your P12. Next, we can get your P21. For your reference, you have P21. So you have row 2 and then column 1. So we're going to get now for your P21, we're going to look at your second row, which is this one here, and your first column, which is still this one here. So your P21 is equal to A21 times B11, as you can see here, and A22 times B21 here, and A23 times B31. So you have this one here. Thus your P21 is equal to your A21 times B11 plus A22 times B21 plus A23 times B31. Lastly, we can get your P22. So for P22, just for your reference again, we're going to take row 2 and column 2. So row 2 and then column 2. So your P22 is equal to A21 times P12 here plus A22 times B22 here plus A23 times B32 here. So your element P22 is equal to A21 B12 plus A22 times B22 plus A23 times B32. So that is how you're going to do the multiplication of your matrices. Multiplication of more than two matrices follows naturally and is associative. So you can do A times B times C, that is equal to your A times B times C. So it's associative. For example, evaluate P, which is equal to your matrix A times B, and Q, which is equal to B times A. Do you think these two are equal? So here your matrix A is this matrix with these elements here, and your matrix B with these elements here. So let's get first your matrix P, which is equal to A times B. So this is a 3 by 3 matrix. This is also a 3 by 3 matrix. Thus we can multiply the two matrices since they have your K. Both K is equal to 3. So first we have your 3 times for your P11. So you have 3 times 2 plus 2 times 1 plus -1 times 3. So we have 6 plus 2. So that's 8 minus -3. So that's 5. And you can do the next steps and you get the following matrix here. So your matrix P has these elements. And similarly, let's do for your matrix Q, which is equal to B times A. So we first write your matrix B and then you write your matrix A. And you get this answer here. And as you can see, your matrix P is not equal to your matrix Q. That means that these results illustrate that in general, two matrices do not commute. That is, your AB is not equal to your BA. So they do not commute. You can pause this video to verify the answers by solving the matrices, the multiplication of the matrices yourselves. Matrix multiplication is distributive over addition. That is, if you have your A plus B times C, so you can just distribute your C, so you have AC plus BC. But again, this is not equal to your C times A plus B because again, your multiplication of matrices is not commutative. Or yeah, they're not commutative. So your C times A plus B is equal to CA plus CB. And remember that AC is not equal to CA and BC is not equal to CB. The null or a zero matrix, 0, has all the elements equal to 0. So for example, you can write your null matrix like this one. You have 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is a 3 by 3 null matrix. So all the elements are equal to 0. So its properties are the following. So if you have A times the null vector or the null matrix, so you have A times 0 is equal to 0, which is also equal to 0 times A. And if you have A plus 0, this is equal to 0 plus A, which is equal to A. So that is the property of your null matrix. The identity matrix I, on the other hand, has this property wherein if you have your matrix A multiplied by the identity matrix I, or you have your identity matrix I multiplied by your matrix A, that's just equal to your A. And you can look at your your identity matrix with this form. Okay, so the n by n identity matrix, often denoted by in, has this following form. So we have 1, 0, 0, 0, and then 0 here. So what you see is all the other numbers are 0 except for this diagonal. So for your diagonal, um, you have your elements equal to 1. Okay, so if this is a 3 by 3 matrix, for example, your identity matrix is this one here. You have your 1, 0, 0, 0, 1, 0, 0, 0, 1. So the diagonal elements have values equal to 1 and all the rest are zeros. This is your identity matrix. Some functions of your matrices. If a matrix A is square, then one can define powers of A in a straightforward way. For example, if you have A squared, then that's just equal to A times A. If you have A cubed, that's equal to A times A times A. Or in general, if you have A to the n, that's equal to A times A dot A. You multiply A n times, where n is of course a positive integer. And we may construct functions of A of the form, you have S, that's equal to the sum of your an from n, where here the ak are simple scalars and the number of terms in the summation may be finite or infinite. Next, let's discuss the transpose of a matrix. So the transpose of a matrix A is denoted by AT. So T meaning transpose. So the transpose of a matrix A is denoted by AT and is formed by interchanging the rows and the columns of A. So for example, find the transpose of this matrix here. You have 3, 1, 1, 0, 4, 1. So again, what we do is we interchange the rows and the columns of your A. So by interchanging the rows and columns of A, so this will now be, instead of that this one is your first row, this will become your first column, and this will become your second column. Okay, so interchange the rows and the column. So your first column now will be your 3, 1, 2, and then your second column will be 0, 4, 1. So that is the transpose of your matrix. So you just interchange the rows and the columns of A. The transpose of the product of two matrices, you have A, B, T, is given by the product of their transposes taken in the reverse order. That is, if you have A times B and then you transpose this one, that is equal to the transpose of B times the transpose of A. Okay, so that is given by the product of their transposes taken in the reverse order. And you can extend this one to the product of several matrices to give this equation here. So if you have, say, for example, A times B times C dot times G transpose, then we take the reverse of this one. We start with G, and then we go up to A, and we take the transpose of each individual matrices. So that is the transpose of the product of two matrices or of several matrices. Now let's discuss the complex conjugate denoted by your A star. So if you remember our lesson on complex conjugate on your complex number, that is just, we are going to apply that concept here. So the complex conjugate denoted by A star is the matrix obtained by taking the complex conjugate of each of the elements of A. That is, the complex conjugate of your A star, Aij, is equal to the complex conjugate of each of the element of your matrix A. So that is Aij star. And obviously, if a matrix is real, it contains only real elements, then your A star is just equal to your A. So nothing happens if you have a real matrix. For example, find the complex conjugate of this matrix. So again, what we do is to get the complex conjugate of each of the elements. So this is a 2 by 3 matrix. So you have 2 rows and 3 columns. So you have elements 1, 2, 3, I, 1 plus I, 1 and 0. So first, what's the complex conjugate of 1? That's just a real number, so that's just 1. Complex conjugate of 2, that's just 2. It's a real number. The complex conjugate of 3i is negative 3i. This is now a complex number. The complex conjugate of 1 plus I is equal to 1 minus I. For 1, it's just 1. And lastly, for 0, that's 0. So this is the A star or the complex conjugate of your matrix A. For the last topic of this video, let's discuss the Hermitian conjugate of a matrix. So the Hermitian conjugate, or you can also call this one as the adjoint of a matrix, denoted by your A dagger. So this symbol here, you read it as your dagger. So it's a literal dagger, is the transpose of its complex conjugate. So you have two keywords here. You have transpose and then your complex conjugate, or equivalently, your complex conjugate of its transpose. So what you do in order to get the Hermitian conjugate or the adjoint of your matrix is by transposing first your matrix, and then for the transpose you get the complex conjugate of the individual elements, or you can also get first the complex conjugate of the individual elements, and then after that one you transpose your matrix. That is your A dagger is equal to A star T. The transpose of your complex conjugate, or that's equal to A star, the complex conjugate of the transpose of your matrix. And we note that if A is real, and so your complex conjugate of your A is just equal to A, then your A dagger is equal to the A transpose. This is the case only for your real A, okay? And the Hermitian conjugate of a product can be shown to be the following. So you have a times b dot times g dagger. So that's equal to your g dagger plus dot times b dagger times a dagger. So remember that this is what you do when you multiply or you get the transpose of the product of your separate matrix. You reverse the order, and then you get the Hermitian conjugate of your individual matrices. For example, find the Hermitian conjugate of this matrix here. You have 1, 2, 3, I, 1 plus I, 1 times 0. So we have already solved for the complex conjugate of this matrix earlier. So what we did again was we got the individual complex conjugate, and then for this one here, for this example, you're going to find the Hermitian conjugate. That is, we transpose now the matrix with your the matrix where we got the complex conjugates. So taking the complex conjugate of A and then forming the transpose, we find that your A dagger is equal to this matrix here. Okay, so again, let's just solve it. For your A star, that's equal to 1, 1 minus I, 2, 1, and then negative 3i, and 0. And after that one, we are going to reverse your rows into columns. So instead of having this one as your first row, this will now become your first column. And then instead of having this one as your second row, This will now become your second column. So you have 1, 2, negative 3i, your first row that become your first column, and then your 1 minus I, 1, 0, your second row, which is now your second column. If we obtain the same result, of course, if we take the transpose of A and then the complex and take the complex conjugate, we get the same answer. Okay, so that ends the topic for this video. So in the next lesson, we're going to continue with our discussion on your linear or in your matrix algebra.